Okay, so in this next part, what we're going to start doing is talking about these ways of evaluating relative standing. How do we compare different data points within a data set to each other? So one method, we're going to talk about several methods, but one method is in calculating z-scores. Z-scores are a measure of relative standing. A z-score is found by converting a value to a standardized scale as given in the following definition. So in this definition, what we have is the z-score is the number of standard deviations that a particular value in a data set is above or below the mean. Okay, so the z-score is how many standard deviations a particular data point is above or below the mean. And so if we're talking about the z-score of a sample, z is equal to the data point, x, minus the mean of that sample, divided by the standard deviation of the sample. And then in the population, the z-score is the data point minus the mean of the population divided by the standard deviation of the population. Okay. And then in terms of rounding off rules, with z-scores, what we want to round to is 2 decimal places. We always want to round up to 2 decimal places. So don't round up, for example, to 2.3, but we do 2.331. So there are some important properties of z-scores. A z-score is the number of standard deviations that a given value x is above or below the mean. The z-scores are expressed as numbers with no units. Okay? And a data value is considered significantly low if its z-score is less than or equal to -2, or if the z-score is, the value is significantly high if the z-score is greater than or equal to 2. Okay, remember, 2 or -2, that means that value is either 2 standard deviations below or 2 standard deviations above the mean. And that's our definition of significantly high or low. So the z-scores really simplify that to tell us whether it's something is significantly high or low. Okay. And so if a data value is less than the mean, the z-score will be negative. If the data value is above the mean, the z-score will be positive. So z-scores are helpful. It helps us see significance, high or low, and also helps us determine whether that value is below the mean or above the mean. So let's practice getting a z-score. So which of the following 2 data values is more extreme relative to the data set where it came from? So we've got a birth weight. We've got a newborn baby that's 4,000 grams, right? 4 kilograms. And it's born in now it has it's in a data set where the average weight of that data set was 3,152 grams. Okay? And the standard deviation of that sample was 693.4 grams. Okay? So a baby born in a group of a sample data set where it was weighing 4,000 grams. The mean for that data set was 3,152 grams. The standard deviation was 693.4 grams. Now let's look at body temperature. We have a body temperature of an adult that's 99 degrees Fahrenheit. And it's in a data set among 106 adults. The sample mean was 98.2, and the standard deviation was 0.62. So we're comparing, notice what we're comparing. Z-scores help us do this. Z-scores don't have units. So we're comparing birth weight to body temperature, 2 very, very different measures. Now, for the birth weight, the way we calculate this, we look at the data point minus the average for the sample divided by the standard deviation of the sample. So that birth weight, that baby was 4,000 grams minus the mean of 3,152 grams divided by the standard deviation, which was 693.4 grams. That gives us a z-score of 1.22. Remember, we rounded off to 2 decimal points. Body temperature. We had 99 degrees Fahrenheit minus the average of 98.2 and divided by the standard deviation of 0.62. That gives us 1.29. So this tells us that the z-score for the birth weight is less than the z-score of the body temperature. Right? The z-score of the birth weight is 1.22 standard deviations above the mean, and the 99 degrees Fahrenheit body temperature is 1.29 standard deviations above the mean. Right? We know they're above the mean because they're positive numbers. So we can tell that the body temperature is a little more extreme than birth weight. It's not huge, but it's a little bit more outside of the norm than the birth weight. But we also know, because these are less than 2, we know it's not significantly higher than the mean. So we can use z-scores to easily identify significant values. And we can use the range rule of thumb. So significantly low values are going to have z-scores of equal to or greater than -2. And significantly high values are going to have z-scores equal to or greater than +2. Okay. So let's look at this, practicing a z-score to find significant values. So let's ask, again, these body value data set from the textbook, platelet count. So we have a platelet count of somebody with 75. Is that significantly low? It's low, but is it significantly low? So the average for the data of the people in that data set was 239.4. That was the average platelet count. The standard deviation of the platelet count was 64.2. So our subject had a platelet count of 75. 75 minus 239.4 divided by 64.2 gives us a z-score of -2.56. -2.56 tells us that that person's platelet count is 2.56 standard deviations below the mean. We know it's below the mean because it's negative, and we know it's significantly low because it is -2 or more. So we know that 75 is significantly low compared to the mean. Another way of measuring relative standing of values in a data set is percentiles. Percentiles are one type of what we call quintiles or fractiles. Percentiles are going to partition a data set into groups with the same number of values in each group. So a percentile measures the location. So we denote the percentile as capital P sub 1 to so forth, all the way up to 99. There's going to be 99 percentiles in a particular data set. And that's going to divide the group into 100 little groups with exactly 1% of the values in each group. And the percentiles are going to be in order of magnitude. Okay? So if a data point is in the 99th percentile, it means that 98% or 99% of the values are less than that particular value. Okay? And only 1% of the data was greater than that particular value. A 50th percentile, which is denoted by P50, has about 50% of the data points below it and 50% above it. So the 50th percentile is actually the same as the median. So how do we find the percentile of a data value? The process for finding the percentile is going to be equal to, so we want to find the percentile of a particular data X. What we do is we get the number of values less than X. We put the values in order of magnitude. The number of values less than X divided by the total number of values times 100. And that's going to give us our percentile. So let's practice that. In this table, what we have is measurements of codeine. This is the measure of basically nicotine in individuals who were not smoking themselves but had exposure to secondhand smoke. And so this was the data values for the blood levels of nicotine. So what we want to know is for the level of nicotine that is 198 nanograms per milliliter, what percentile is that for the group? 198. So 198 is right here, right? 198 is right here. So the list is already sorted, and what we see is that there are 22 values less than 198. There were 22 values less than 198. So to calculate the percentile of this data value, 198, we do 22, because it's in position 22, divided by 40, because there's a total of 40 values, times 100. That gives us a number 55. So that codeine level, 198, is in the 55th percentile. Okay, 55th percentile. So that means that 55th percentile, so it's just above the 50th, just above the median. So converting, we could also go in the opposite direction. We can also ask, what value in the data set is sitting at a particular percentile. So sometimes you want to know what value in the data set is our 25th percentile, for example. And we can do this by converting a given percentile into the corresponding data set. So let's say we want to know what codeine level represents the 33rd percentile. Okay? What is the codeine level that represents the 33rd percentile? So there is a procedure for being able to determine what point in our data set corresponds to a particular percentile. Okay? And so this is the procedure, and we're going to walk through this right now. But before we walk through it, we have to define some of the notation. So n, we know, is the total number of values in the data set. In this example, k is the percentile being used. So if we're looking for the 33rd percentile, k is 33. If we're looking for the 25th percentile, k is 25. The L stands for locator. That gives us the position of the value that we're looking for. Okay? If we have 40 values and we want to look for the 25th percentile, we want to know which position out of 40 represents that 25th percentile. That's what L is. So we want to find L in order to find the position. And then P sub k is the kth percentile, right? So k being the percentile we're looking for, P sub, if it's a 25th percentile, then P sub 25 is the 25th percentile. So the process we start with, number one, we have to sort the data in order of magnitude. Then we want to find L. We want to find the locator. So we do that by taking K, our percentile that we're looking for, divided by 100, and then multiplied by N, which is the number of values in our data set. Now that number for the locator, that's going to give us the position. Now we do different things if that position is a whole number versus the position is a not a whole number. So if that position is a whole number, then what we want to do is we want to find the value in that position, and then we want to find the value in the next position. So if we find that the value is the L is 12, we want to take the value that's in the 12th position and also take the value in the 13th position. And we're going to add those values together and divide by 2. Okay? Because if the L is a whole number, then the percentile value is actually sitting between that one and the next one. But if the L is a fraction, if it is not a whole number, we round to the next number. So let's say we get L and L is 12.3. We round 12.3 to 13, and then that value that's in the 13th position, that is our percentile. Okay? So let's do an example of this. Let's do an example. So we're looking for the 33rd percentile in this table of codeine levels. So number one, the first step was sorting it in order of magnitude. It's already done for us, so that's great. So then we can move on to finding L. L was equal to the K, which is the percentile we're looking for, over 100 times N. K is 33. We're looking for the 33rd percentile. 33 divided by 100 times 40, because there's 40 numbers, equals 13.2. Okay? Now 13.2 is not a whole number. So remember, what we need to do now is round up to the next number. So 13 gets rounded to 14. So the 33rd percentile is going to be in the 14th position. And the value that's in the 14th position is this one, 122. We count from the bottom up, and the 14th position is 22. So that means that the 121 is in the 14th position. So that means 121 represents the 33rd percentile. So that means that 33% of these codeine levels were below 121 and 67% were above 121. Okay. So because we had the L was 13.2, we rounded to 14 and we looked for our 14th position, and that was our 33rd percentile. If L had turned out to be a whole number like 13, then what we would do is we would find the 13th position, which is 112, add it to the 14th position, okay, and divide by 2. I think I said that wrong. Let's say the L had turned out to be 13. Okay, we would find the value that's in the 13th position. That's 121. I didn't say it wrong. And then we would also look at the one that's in the next up position, 121. We add 112 to 121 and divide by 2, and that's the value in our percentile. Okay. Similar to percentiles is something called quartiles. So there are 99 percentiles that divide a data into 100 groups. And there are 3 quartiles that divide the data into 4 groups. Basically, a quartile is slicing up the data into, 25%, 50, 75, and 100. Okay. So quartiles are measuring the location of the first quartile, which is the 25th percentile, second, which is the 50th percentile, and the third is the 75th percentile. And that divides the groups up into 4 groups. So the first quartile is the same as P25 or the 25th percentile. Second quartile is the same as P50, which is the 50th percentile. And the third quartile is P75, which is the same as saying the 75th percentile. Okay. Once we get our quartiles, we also can define other measures. So we can get what's called the interquartile range. So that is basically, we take the first quartile and the third quartile and then we subtract them. And that tells us the distance. Interquartile range tells us the distance between the first quartile and the third quartile. The semi-interquartile range is just half of that interquartile range. So we take the third quartile subtracted by the first quartile and divide by 2. That gives us half of the interquartile range. We can also find the mid-quartile. Okay? So the interquartile range is the distance between these two values. When we look at the mid-quartile, what we want to know is what is the value in the middle between the first and third quartile? What is the distance, not the distance, what is the value that sits at the middle between the first quartile and the third? So what we're doing, instead of subtracting, because we're not looking at the distance, we're just looking at the actual values, we add the third quartile to the first quartile and divide by 2. And that gives us the one that's in the middle. And then we can also look at the 10 to 90th percentile range. That gives us the distance between the 10th percentile and the 90th percentile. So just different ways of summarizing our data and data in relation to each other. Another way of summarizing data is doing something called a 5-number summary, which then once we have a 5-number summary, we can construct something called a box plot. So in a 5-number summary, we have a data set and we want to sort of summarize things about our data. What we can do with a 5-number summary is we give the minimum value, we can give the first quartile value, the second quartile value, which is the same as the median, the third quartile value, and the maximum. Okay. Now, instead of just looking at 5 numbers, we can actually construct a diagram, a graph called a box plot. But first, let's see how we get those 5 numbers. Let's practice this. So let's find a 5-number summary for our coditine table. So the minimum value, right, on this coditine table is 0. Minimum value is 0. Our maximum is 491. Okay. Our first quartile, if we use the same process as finding the percentile, so we're looking for the 25th percentile, so 25 divided by, remember we have to find L, 25 divided by 100 times 40, because we have 40 values, okay, gives us our locator. And when we then decide if the locator is a whole number or a fraction, we can use that method to find our value. So The first quartile is 86.5. Okay? 86.5 is halfway between this value and this value. That's our first quartile. Our 50th percentile, or our second quartile, is 170. Okay? 170. 170 is midway between this value and this value, 167 and 173. And then our third quartile is our 75th percentile, and that's 251.5. 251.5 is halfway between 250 and 253. So those are our 5-number summaries: 0, 86.5, 170, 251.5, and 490. So we can take our 5-number summary and we can construct a box plot. A box plot is a graph of a data set that consists of a line that extends from the minimum value to the maximum value, and there's a box in the middle that draws and illustrates the distance between the first quartile and the third quartile and shows where the median is, which is that 50th percentile. Okay. So if we go back and we construct the box plot for our 5-number summary of the codidine measures, what we have is the minimum is 0, maximum is 491, the first quartile is 86.5, the third quartile is 251.5, the second quartile or 50th percentile or median is 170. Okay, and that is our box plot. And so it really helps us look at what our data looks like. The box plot can really help us see sort of the shape of the data. It's not exactly a frequency distribution, it's not a histogram, but it can give us a sense of whether the data is skewed. If the box plot is closer to 0, right, the position of the box is closer to 0, then that tells us that our data is right skewed. If our box is closer to the maximum, it tells us that our data is left skewed. So it can, if it's right in the middle, it tells us it's more normally distributed and there's no skew. So outliers are sample values that lie very far away from most of the data points. And when we analyze data, it's important for us to identify and consider the outliers, because they can strongly affect the values of some of our important statistics, like mean and standard deviation. And once we identify the outliers, we can also include them in our box plot to create what's called a modified box plot. So when we identify outliers, the way we identify outliers is first we have to find our quartiles. First quartile, second, and third. We then have to find our interquartile range, the distance between our third quartile and our first. Then what we want to do, once we get our interquartile range, we find 1.5 times the interquartile range. So an outlier is going to be a value that lies either 1.5 times the interquartile range below or above. Okay. So if it's greater than 1.5 times the interquartile range, it's an outlier. If it's less than 1.5 times the interquartile range, it's an outlier. So let's see what this looks like. So when we have this box plot, this is what it's going to look like. We have our minimum, our maximum, we have our first quartile, third quartile, and our median, and our interquartile range. Now this line over here represents our first quartile minus 1.5 times the interquartile range. Anything below that line is an outlier. And then over here we've got our first quartile plus 1.5 times the interquartile range. And that is going to be the line that anything above that is also going to be an outlier. We're going to demonstrate it, but we're going to identify it as an outlier, and we're not going to let these outliers affect our summary of the data. We're not going to let those outliers distort our summary of the data. So let's create a modified box plot. Okay? And let's use the pulse rate data from that set that we've been using. So our 5-number summary for our pulse rate data is 40, 62, 68, 76, and 104. So the minimum is 40, maximum is 104. First quartile is 62, second quartile is 68, and third quartile is 76. So interquartile range is third quartile minus first. So 76 minus 62 is 14. That's the interquartile range. 1.5 times interquartile range is equal to 1.5 times 14, which is 21. So any outlier is going to be 21 points more than the third quartile, or 21 less than the first quartile. Okay. So since the first quartile, the first quartile is 62, anything 21 minus 62, right? Anything less than that is going to be an outlier. And since the greatest, our third quartile is 76, anything greater 21 beats per minute or more than 76 is going to be our outlier. Okay, so let's look at this modified box plot. So here we've got our minimum, which is 42, our maximum, which is 96, okay, our first quartile, which is 62, second quartile, which is 68, third quartile, which is 76, okay. Now, we have these outliers, 102 and 104. 96, anything above 96 is going to be an outlier. That's what 102 and 104 are. Anything below 42 is an outlier. So 40, that's an outlier. So we're drawing our outliers, but we're not letting it distort our box plot.